The prefix poly means many. Nomial means terms. So we're literally talking about something that has many terms. Well, what is a term? That's a great question. A term is either a variable, a constant, or a coefficient and a variable. Okay, so those words you're going to be hearing a lot. Some of them are familiar, some of them may not have ever been directly clarified for you. A variable is obviously a letter, right? We know that. A constant is just a plain old-fashioned number. Like if it said +3 at the end of an expression, that's the constant term. And then most commonly, you will see a coefficient and a variable put together. So this is the coefficient, this is the variable. Does anybody know what this is called? It is, well, it is squared, but it starts with an exponent. Very good, yes. So we have, in each term, you can have a coefficient, so a number, a variable, and an exponent. And the exponent will also be a number for polynomials. Okay, there are many types of polynomials we will write. You have actually worked with a lot of polynomials before. Something called a monomial, see that prefix mono means one. So a monomial is just like a regular term x. It has one term. If we add the prefix binomial, how many terms are probably going to be in that if it says binomial? 2, like a bicycle has 2 wheels. A binomial is going to look something like this. Terms are separated with pluses or minuses. So x plus 5 is a binomial because it has a variable and a constant. Oop, I wrote the wrong word. This should say 2 terms. So x and x plus 5. If we go to trinomial, how many terms are there? 3. So maybe something like this, x squared plus x plus 5. That is a trinomial because there are 3 terms. We have a variable with an exponent, a variable, and a constant. 3 terms. But let me tell you, after that, mathematicians got lazy. We didn't start doing quadnomials or quintinomials. We just started calling them polynomials. So they're all polynomials. We specifically name monomials, binomials, and trinomials, and after that, we don't care about the names. So a polynomial can be something crazy like x to the 5th plus x to the 4th plus x to the 3rd plus x to the 2nd plus x plus 1. Just as long as it has many terms put together, it is technically a polynomial. We just don't name it specifically for the number of terms in it after trinomial because we're over it. Now there's an important note here. The polynomials in the variable part of each term cannot be underneath a radical or underneath a denominator. So they just need to be plain variables, not looking like this. So if you see your polynomial has something like this or like this, it is no longer a polynomial. So just be aware of that. It's not like I won't show you those, but just so you know. Now, polynomials should be written in what's called standard form. Standard form is what most textbooks and most mathematicians, actually all mathematicians, will write their final answers like this. It's called decreasing exponent order. Literally, all that means is that the exponents are going to get smaller from the beginning to the end. Look, we started with the exponent of 4, exponent of 3, exponent of 2, exponent of 1, and then like biggest to the smallest of the exponents. I don't care about the coefficients, I'm caring about the little floaty numbers. Those need to be from biggest to smallest, and that's called standard form. Most of the time, the polynomials that I give you will be in standard form. I also request that polynomials you give me are in standard form, but occasionally they'll be out of order, like that non-example, where if you look, the first thing we started with was power of 2, and then we went up to power of 4, and then we went to a constant, and then we had power of 3, and then we had power of 1. Ugh. Let's put it in order, okay? So all you have to do is literally pick them up and put them in order. 4, 3, 2, 1, 0. Yeah. Now again, most of the ones I give you will be in standard form to begin with, but just be aware that that's a possibility. One more thing we need to remember before we really get into polynomials is this exponent rule. It's called the product of powers property. This is super duper important. If you were to highlight, circle, star, underline anything today, this probably would be the most helpful. It's something we learned probably in 8th grade forgot about, relearned in 9th grade, probably forgot about, and have touched on in this class already, but just to say it one more time, the product of powers property means that if you are multiplying things that have the same base, you just add their exponents. Meaning, if I was multiplying 3x to the second power times 4x to the third power, I would multiply those purple numbers because they're coefficients by each other. So I would do 3 times 4, which is 12. But in the exponent, I don't multiply them. In the exponent, I add them. So we don't want to multiply the exponents together. We want to add the exponents together. So this would actually be x to the 2 plus 3 power, because we want to add those exponents, which would really just be 12x to the 7. Wow, did I really add? I just wrote a 5. That should be a 3. My brain got ahead of my hand. So big numbers, treat them like you always do. If it says multiply, multiply them. But little numbers, you don't do the normal thing. If you're multiplying, you add them. And when you're dividing, you subtract them, which we've done before in this class. So all of this to say, this is all like pre-information for us to be able to actually do arithmetic. The first 2 things we're doing are going to be very easy, adding, subtracting. And multiplying, also decently easy. It is going to feel very similar to when we did complex numbers. The thing with the I, do y'all remember doing the stuff with the I? Where we added the reals with the reals and the imaginary with the imaginary? Ooh, not ISS, not isolate, separate, solve, but that's a good idea. What we're going to do is we're just going to add and subtract these polynomials together. We're going to make them look like an old school elementary style addition problem. Meaning, I'm going to take this add sign and be like, okay, great, I'm going to be adding these polynomials together. Let me make it literally line up like an old school addition problem. So I'm going to take the entire second parentheses and I'm going to write it underneath the first parentheses, making sure that I line up the variables and the exponents together. So all I did was take this side and drop it right here. And I made sure the x squareds went with the x squareds, the x's went with the x's, and the constants, regular numbers, went with the constants. Do y'all see how they're lined up? Great, and it says to add, so guess what I'm going to do? I'm literally going to add. Straight down like an old-fashioned math problem. Meaning I would do negative 4x squared minus 1x squared. Well, that's negative 5x squared. I would do negative 6 plus 7x. Well, negative 6 plus 7 is 1, so plus 1x. And then I would do 18 plus 8. 18 plus 8 is 26. Voila, I'm done. That's it. It's just literally combining like terms. So if you want to write CLT for yourself, combine like terms, that's all we're doing when we're adding polynomials. They need to be alike, x squared with x squareds, x's with x's, constants with constants. Just like we did real with real, imaginary with imaginary. Bloop, drop them down. Okay, adding is so easy. I don't even have another example for y'all. But we're going to do some subtracting because subtracting has one more step before we combine like terms. We need to make sure that we take this minus sign and we distribute it to every single minus sign and plus sign in the second term. But all that does is change the signs. Subtracting is adding the opposite. So when I write this down underneath to line them up, I just write down the opposites. What's the opposite of negative 11x to the fourth? Positive 11x to the fourth. Great. Let me write that in a different color. You change all the signs. So what's the opposite of positive 5x squared? Now question, where do I write the negative 5x squared? Well, do I write it here? Oh, why not? It's not like terms. Very good. Where would I write it? Underneath that negative 3x squared, because I need the x squareds to line up. Boom. Good eye. Now that we notice that, you have to line them up correctly. Do you see that? Okay. Instead of negative 7x, when I write it down, what am I going to write? 7x. Positive 7x. And then instead of positive 13, negative 13. But once I've done the opposite, it turns into an adding problem. So subtracting is just distributing and adding. And so we add negative 11x to the fourth plus 11x to the fourth. What happens there? You got a negative 11 and a positive 11. 0. They cancel out. Great. This doesn't have anything to combine with. You just drop it down. So we're going to start our polynomial off with negative x cubed. Negative 3x squared plus negative 5x squared is negative 8 x squareds. 10x plus 7x is 17x. And negative 2 minus 13 is negative 15. Great. So if we were going to write down 2 words to describe the steps we did, what would be the 2 words, one for each step? Distribute, that was my blue step, very good. And what's the second one? Well, I guess it's not a word, it's an acronym. Yeah, I think you're trying to, yeah, perfect, combine like terms, CLT. That's it for subtracting. So it's almost basically an addition problem as long as you add the opposites. Okay, question number 3 is for you to make sure you got it. So remember, this one says subtract. Don't try to add when it's asking you to subtract. So we distribute, then we combine. I'll give you a second. Keep working if you're working, but I'm going to start writing mine on the board so you can see. Okay, take a look at the board. How'd we do? Remember, when you write them down and we're subtracting, don't write the same sign as before. All of these signs need to change. So instead of positive x squared, it's negative. Instead of negative 2x, it's positive. And instead of negative 4, it's positive 4. So you just switch the signs and bloop, 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 add them up. How do we feel? Even if we didn't get that right, does the process make sense? We distribute, we combine like terms. Cool, cool, cool. Adding, subtracting, check, done. We've already done 2 of the 3 things we're doing today. And now we're going to multiply them. Multiplying can be either really easy or very difficult. If you have bad handwriting, I need you to take your time and write neatly. This is one of the things where writing with bad handwriting is going to mess you up, because there's going to be things all over the place. So write with your best handwriting possible to multiply polynomials. In number 4, we are multiplying a monomial, one term, times a polynomial, many terms. These are the easy ones. These are like, yay, I want to do these because they're so easy. Because all we're doing when it's a monomial times a polynomial is we are distributing. And thus, the only thing we have to remember is that power rule, the exponent rule from the front of our paper, which means we're not multiplying those exponents together. What are we doing with the exponents? Adding them. Heard it. Thank you. Okay, so we go. The first one. 2x squared times 2x cubed. Well, 2 times 2 is 4. And x squared times x to the 3rd power is x to the 5th power. 2 plus 3. Bless you. Then we do the next one. 2x squared times negative 1x squared is going to be negative 2x to what power? 4. 2 plus 2 is 4. So that one now becomes 4. They should be getting bigger because we're multiplying by an exponent. So boop, boop, should be getting bigger. Okay, the next one. The coefficients, we have 2 and 3. 2 times 3 is 6. Easy peasy. And then we get to the exponents. This is going to be x to what power?
2.
Oh, I heard 2 and I heard 3. One of those is correct. Why 2?
Because there's no exponent.
Ooh, there's no exponent showing.
1.
That sneaky invisible exponent is there. Yeah, don't let that trip you up. If you need to write that invisible exponent there so that you know it's there, that's fine. Because it's going to get you if we forget about it. You're right, there's no exponent showing. So now, what was the correct answer? 3, yeah. So x squared times x, it should get bigger every time. Becomes 3. Okay, great. And then we just have our constant at the end. 2 times negative 5 is negative 10. And since there are actually no exponents here because there's no variable, it's just x squared. Okay, that was great. I'm glad we fell for my trick that I put in here so that we remembered about that invisible exponent. Cool. Monomials times polynomials, very easy because that's it. We're done. But when we take anything like a binomial times a binomial or bigger, we're going to need to organize our thoughts. Now, you would have maybe seen this last year in Algebra 1, or maybe 2 years ago in Algebra 1. It's called the Punnett square method. Do y'all remember that at all? Do y'all remember Punnett squares from biology? It's the thing with the alleles where you're like, am I going to have blonde hair or brown hair, depending on what my parents had? And it's like, there's like a probability having to do with the crossing of the alleles. Okay, so basically, we're going to use the idea of Punnett squares for this problem. Because this problem is saying x minus 7 squared, which is really like saying x minus 7 times x minus 7. This is a binomial times a binomial. This would be a FOIL question if you liked foiling whenever we did complex numbers. I like the foiling method, but when we get to polynomials, if they get bigger than this, it's just disastrous. So we might actually want to use this Punnett square method. But what we're going to do is we're going to list the first binomial on the top of the Punnett square, x and negative 7. We're going to list the second binomial on the side of the Punnett square, x and negative 7. Do we see how I did that? So whatever the first little parentheses is, put it on top. Whatever the second parentheses is, put it on the side. Cool. We're going to cross these, which means we're going to do 4 multiplications. The first box would be x times x. What is x times x? Oh, I heard it. To the power of 2. Remember, invisible exponent, we add them. 1 plus 1 is 2. Okay, this next box right here would be x times negative 7. Well, that's negative 7x. Boom, done. The next box, if you look at the grid, would be negative 7 times x. We just did that, so that's negative 7x. And then the last box, what are the two things I would multiply together? Times, yes sir, negative 7 times negative 7. Positive 49. Remember, we actually multiply those. When they're just regular numbers, you actually multiply them. Okay, great. Do you notice anything, especially because I use this color coding, about the things on the diagonal? What do you notice about these two things? They're the same. What do we do with things that are the same? We combine them. We add them. Look, there's a whole plus sign in the middle of them to help remind us that we add those two things together. Negative 7 plus negative 7 is negative 14x. So to finish this problem, you just take all of the numbers out of the box. Well, we already took the diagonal out of the box. All that's left is the x squared in front of it, the negative 14 that we took out, and that positive 49. Voila. We multiplied a binomial times a binomial and got a trinomial. Amazing. Okay, I'm going to have you try part of the next question on your own, but it's just this process. So before I do that, do we have any questions about the Punnett square? No? Okay. Now this next question, you all are just doing part 1 on your own. I'm going to help you with the second part because you notice there's 2 boxes here. I did that on purpose. We have a binomial times a binomial times a binomial. We're going to pretend, don't mark this out on yours because I can erase, I know you can't. Pretend like this doesn't exist for a second. Don't mark it out on yours, like I said, because we need it. How would you fill out the first Punnett square if that's the only problem you had?
X.
On the top, okay. And 2 or?
Negative 2.
Negative 2. Okay, great. I want you to do this Punnett square, and only this Punnett square for me. So we cross them. So you should do 4 individual little multiplication problems. I'll give you a second. Okay, if I were crossing this one, here's what I would do. The first box is x times x, so x squared. The box next to it is 1 times x. That's 1x. And I'll show the 1 there right now. And then the next box at the bottom is negative 2 times x, so that's negative 2x. And then negative 1 times 1, which is great. I still have like terms on the diagonal, so I know that I would add those together. And if I forgot, it's like literally there's a plus sign right here reminding me. Great. Which means the things I would get out of this is negative 1x. It would be x squared minus 1x minus 2. Fabulous. Here's a problem we're not done, because this was just the first part of this problem. You guys successfully did the binomial times the binomial. But remember, we're multiplying it by one more binomial that I had covered up earlier. So we're going to take what we got as this answer. We're going to write it up here so that we have the x squared, the negative x, and the negative 2 on the top. What do you think goes on the side? X and 6. The other little binomial that I need to multiply it by. Because it's in the problem. Yeah, the OG problem. I just forgot about it for a second. And now I'm using it. Okay, great. My Punnett square got bigger, but the process of using the Punnett square does not change. I'm still going to do box by box. So in this first one, I'm going to do x times x squared. What is x times x squared? X to the third. Yes, x cubed. Remember, it has to get bigger every time. Yeah, and there's an invisible 1 right here. Maybe it's helpful to write it. Here, I'll write it on both. The next box would be negative x times x, right? Well, negative x times x, negative x squared. Very good. The last box would be negative 2 times x, which is negative 2x. Whew, okay. Next row. We would do 6 times x squared. What's 6 times x squared? 6x squared. Very good. Ooh, I used the wrong color. The next box would be 6 times negative x. Negative 6x, because there's only one x, so it doesn't have to get bigger when you're only multiplying by a single x. And then the last one is 6 times negative 2. Those are just numbers, negative 12. What do you notice about this longer Punnett square? What is still happening on your diagonals? My like terms are still on a diagonal, so I'm still going to add them. Your diagonal got longer. That's okay. We're going to add them. The blue ones, the x squareds would become 5x squareds because you have 6 and negative 1. The green ones would become negative 8x because they're both negative, so you add the numbers, keep the sign. And then we just take all of the numbers out of the box, and we have our final answer. The final polynomial here would be x cubed plus 5x squared minus 8x minus 12. Woo-wee. So even if the problem has multiple parts, each individual part, not that hard. They're just longer problems. But that's why we use the box to keep ourselves organized. If we were to foil or double distribute these, first of all, it would take you like a half piece of paper to keep it all organized. Nobody wants to waste that many trees. So we use the Punnett square to contain it all. The Punnett square then becomes extremely helpful when you have a monster problem like this one. Oh boy, we're going to do a trinomial times a trinomial. Not a big deal, though, because the Punnett square tells me exactly what to multiply. Corey, what should I write on the top of this Punnett square? Tell me what exactly. Okay. Great. And 25. Great. So, Les, what should I write on the side of this Punnett square?
3x squared to 6x, negative 6x.
Okay. Great. Cool. I still have individual spaces on this Punnett square for me to multiply them. We start off slowly. Start at the top corner. We have 3x squared times x squared. That would be 3x to what power?
4.
4. Very good, because we add those exponents. 2 plus 2 is 4. The next box would be 3x squared times negative 10x. Negative 30x to what power? 3, very good, because remember, you've got that invisible 1 right here. We'll go ahead and write it in, because I think that's helpful for you guys. Okay, last box on the top row, we have 25 times 3x squared. 75. X to what power?
2.
Trick question. It's just 2. Yeah, there's no other x to make it bigger, so it stays the same. Can you all finish this Punnett square for me? I'll help you finish out the entire problem if you need help. I think some of us might be able to see what's happening here. I want you to finish the Punnett square for me. Okay, I might have gone a little bit faster than you, but is this what your Punnett square looks like? This is one of those types of problems where making a silly, like, little mistake frustrates you because the whole thing becomes wrong. So really take your time on these. That's the Punnett square with the organization is really the only way to go. But what do you notice about this giant box and its diagonals? Is this diagonal still the same type of term? Is this diagonal still the same type of term? And this one? Oh, snap. Those are the things we have to combine together before we finish. So the diagonals will still help you. And because of the hint right here where it's cross, we know we're going to add all of these things together to get three numbers that we're going to pull out of the Punnett square. The blue number we would pull out, and I'm going to draw an arrow because I don't want to get it all messed up. Negative 36 and negative 6 is, wow, I said the answer out loud. Negative 30 and negative 6 is negative 36 x cubes. The green number, 75 plus 60 minus 1 is 134. And then negative 150 plus 10 is negative 140. So we take all of the numbers out of the Punnett square. 3 of them are already out. We just need the ones that are by themselves to make our final polynomial. Our final polynomial would be 3x to the 4th minus 36x cubed plus 134x squared. I need more room. Minus 140x minus 25. So we took a trinomial times a trinomial and we made a polynomial of degree 4. Pretty cool. Overwhelming because it's such a big polynomial, but the individual pieces, do we understand the process at least? Yeah. Main goal is to be able to do like binomial times trinomial or binomial times binomial, so this would be a push problem. Okay. Last but not least, and we're not actually going to solve this one, we're just going to write an equation. But kind of understanding why we even do this type of polynomial work is this question right here. It says, a rectangular pool has a level floor. Okay, pause. Rectangular. When you're talking about a rectangular pool, do we know what kind of shape that is? First of all, a pool, is it 3D or 2D? Like a pool. Like when you get in a pool, can you get in a pool?
3D.
It's 3D. 3D means it's got a length, a width, and a height. Okay, so if I'm drawing this pool, it's going to look something like this. And you can do your best kind of geometry drawing here too. Here's my swimming pool. Not my best. It'll work. So we have this pool that's rectangular in shape. The length of the pool is 3x minus 1 feet. So let's label that. The length of the pool, I feel like length is this dimension. Okay. The width of the pool, so how wide the pool is x plus 6. And the depth of the pool, what is depth? What does that word mean? Add an extra E in there. What does it look like? Instead of deep, it looks like the word deep, right? It's talking about how deep it is. The depth is x plus 6. It wants me to write an expression for the volume of the pool as a product of binomials. Not actually multiply them out, didn't have enough room for that, but we want to write the expression. Volume is a geometric measure of how much stuff fits inside of it. Does anyone remember the formula for volume of a rectangle? You would have done this in like 7th or 8th grade, so it's a stretch. No, I haven't thought about that in a while. Does this sound familiar? Volume is length times width times height. Does that sound familiar? Length times width times height. Well, we have all those measurements, do we not? Length, width, and height, or depth. So we can write this expression. The volume of this pool is going to be the length times the width times the height. And if I left you enough room to do this on your notes, it would be exactly like problem number 6 at the top of this page, where you would do 2 of them together, and then do a second Punnett square to multiply them all out again. And we would find an equation for the volume of this pool. Now, why the people who measured this pool didn't actually just measure like 12 yards, 16 yards. I don't know. They measured it in math equations. Probably not the most efficient way to do geometry, but whatever. Here we go. Okay. The goal of today was to be able to be adding, subtracting, and multiplying polynomials. Y'all were like breezing through the adding and subtracting. Multiplying is going to take you some time. And the problems that we've given you for homework, I struggled to do them in my brain because I didn't want to write them down, which means don't tell me you're doing them in your brain. You're going to have to write them down, and it's going to use some paper. So if you need extra pieces of paper, they're in the back. You also have the back of these notes because you could just glue them over your work. You've got a spiral notebook. You've got Post-it notes in my thing. There will be work to be shown for these because you can't do them in your head. I struggled to do them in my head. So you have to show work. When you're adding like these numbers, the blue ones, don't type x to whatever power. Only add the coefficients. So you would type in your calculator -36 plus -6 and then get -36x cubed. Does that make sense? Yeah, just because it's different and the negative is different than the minus sign, so make sure you're practicing with this calculator to get used to that. Okay, fabulous.